So thanks everybody for coming. We are Mach Electric, and today I'm really excited to talk about. We've had some good progress both on the technical side and business development side recently, so should be a good day. Feel free to stop me at any point if you have questions. Kind of a more casual kind of presentation. I always like questions, so we can also do them at the end. So I'll introduce myself first, and Wes as well. I'm the founder. My background is, for the last 10 years, has been in robotics and composites of various types. My PhD dissertation, which I defended last year, was on was on composites for hypersonic spacecraft, specifically for heat shields of probes going into Titan, which is a moon around Saturn, as well as composites of other kinds for aircraft brakes and a whole myriad of others. Along that, Wes and I met while I was doing the engineering management program. Wes doing his MBA a few years ago, and he also is full-time here at CU. And yeah, we've been chugging along together for the last couple of years, and we incorporated Mach Electric in 2023, August 2023. So, yep. We have some other advisors and things that I'll introduce at the end, but I really want to dive right into what we do. Mach Electric, we've got our proprietary technology that takes waste-gas CO2 and turns it into carbon fibers. It's an additive manufacturing process that is a CU spin-out. Wasn't part of my PhD dissertation, but I developed it in my doctoral lab, and we're still working closely in a mentor relationship with my PhD advisor in that laboratory. And essentially, we produce a raw material. So this spindle of I realize that I might be sharing the wrong screen. I think I'm sharing sorry.
Yeah, you can try. I think online people can see both slides.
Oh, they can? Okay.
Yeah.
Yeah. Let me just swap these if I can find how to do that. Sorry, it's hidden behind the Zoom meetings. There we go.
Okay, yeah.
Oh yeah, now it's this thing.
Now it's here. It's fine. This is what's
one or the other. All right. Well, we'll go with this.
Okay. We're happy.
Alrighty. Well, let me actually just share my other screen here. It's gonna be perhaps better. Technology. Sometimes it likes us. Sometimes it doesn't. Share.
Yeah.
Okay, perfect. Let's do that. Pop back up here. Perfect. Alrighty. So why carbon composites? Carbon fiber is a material that many people know, right? It's used in, you see it on Formula One cars, or you hear about it in aircraft, but really, why is it used? It's because it's a very light material that has a high strength to weight ratio. It's advantageous because you can weave it, or you can chop it up and mill it. You can turn it into a type of structure that is dependent on what the application is for. It's a very versatile material, and it's growing in each of these different market segments, among others like outdoor recreation and things like that. In aircraft such as the Dreamliner allows for very long range with the same amount of fuel. It reduces weight drastically, and the same can be said with electric vehicles and wind turbines. Now, that market is growing. 13% is the CAGR as of 2024, and most of that is driven by the aerospace and the wind energy sectors. Almost all of the new wind turbines are made of carbon fiber blades because it allows for a very stiff blade that isn't going to wobble back and forth and hit your tower, but at the same time be as light as possible to generate as much efficient energy. And in our kind of customer discovery within this space, after we've developing the technology, talking with different customers, both within the technical development side, Oak Ridge National Laboratory, for instance, as well as on the industry side on the cutting edge, such as Boston Materials that use carbon fiber, We've seen and heard that there's a growth specifically in this chopped and milled fiber space, as well as in the woven fiber space, but we're going to be focusing on the chopped and milled fiber for our beachhead market. And the other side of this is that we're using waste gas CO2 and sequestering it. And when we talk to European customers, especially within the automotive market, creating carbon negative or carbon neutral materials within the fabrication of the vehicle is incredibly important for these companies, not only for environmental reasons, but also to meet regulation. And so very important within that sector, and we've had some pretty good traction on that front. Now, when we talk about creating these carbon fibers from waste gas CO2, how are we actually doing? What is the unique solution that we're providing here? Well, we bring together 3 independently de-risked technologies, the carbonation of molten salt and splitting that apart via electrolysis. We're not reinventing any kind of new chemistry here. Really what the piece that we're leveraging this de-risked chemistry and bringing in a novel way of deriving that chemistry through additive manufacturing to create a new material, a more useful material in carbon fiber.
What a de-risk technology?
Yeah, so as kind of more a business term of saying that this chemistry there's been about 15 years of both papers and companies utilizing this technology. And de-risking meaning some of the risk in the technology itself, the actual chemistry, has been sought out by others, that a lot of these other research groups and other companies have worked on this chemistry and found the challenges associated with that chemistry and found solutions to that and published papers on it. One of the notable things here is corrosion. Molten salt is very, very corrosive. And my background is high temperature materials for these spacecraft heat shields and whatnot. And that was part of how we leverage some of this de-risked or technology that has a lot of literature on it in mitigating some of that corrosion and how to pump that salt around, how to deal with some of the challenges associated with that. So that's what the term kind of de-risk means, is that you're taking some of the risk out of it by leveraging work that has already been done in the literature.
Yeah, so we're used to, for DoD and other government programs, measuring the level of risk to be able to actually make something out of it by technology readiness on the TRL.
Yep.
What TRL would you assign your process?
Yeah, it's great. So we assign it a level 4 right now. And most of that comes down to that we've proven that the process works in the lab, and I'll show some photos later and two plots of data as well. But we're not at the point that we're scaled up. So we're actually using waste gas CO2 at the moment. We're capturing it from a local brewery, and I have some photos of that as well. But we're not at the production scale. We're not selling it yet. We've had some really, really great conversations with potential customers, people that are very interested in the product. But right now it's still lab scale. I still make it here at CU in a lab. So that's kind of where that TRL4 comes in.
But usually that you haven't worked out the actual manufacturing process. Is that true?
So yeah, it was actually a good conversation that Wes and I had with a potential partner, was that he would say that we're actually more like 5 or 6.
Yeah. That was what I got from
Yeah. I guess to me, like, we've assigned TRL level 4 because we're still in the lab, but we've actually worked out a lot of the technical challenges. There are definitely some, as you scale up, as any kind of process scale up, we're assuming some hurdles that we're going to need to get over, and we've identified a few of those. But the fundamental process, the fundamental additive manufacturing process that the IP and everything is surrounding by, we've actually worked on for about 2.5 years now. So we've massaged out a lot of the issues there, but certainly there is going to be a risk associated with scaling up as any process.
So we've had that discussion earlier. One distinction I made is we're still saying TRL level 4 because, as Spencer said, we're literally in the lab. And the reason we're in the lab is the rent is cheap. And Francisco, Spencer's former advisor, still really likes us. But for us to go from the lab to sort of a modular industrial facility, let's say we just rent out a space, there's no real, to make that jump, there's no real additional technical processes that need to happen. We would just be moving out, and therefore our TRL level would go up. So the prototype itself is pretty robust. It just happens to still be in the aerospace department.
Okay.
Yep.
Um,
And here's just kind of a graphical description of those technologies that we just talked about. Taking that waste gas CO2, putting it through electrolysis, which is very similar if you're familiar with water electrolysis, where you split water apart into hydrogen and oxygen. The process here is very similar. We're taking CO2, we're dissolving it into lithium oxide. That lithium oxide then turns into lithium carbonate. We then split that apart with using electricity. So you get oxygen gas coming off and solid carbon bonding on. And then that lithium carbonate turns back into lithium oxide, and then you can then re-infiltrate it. So that salt, that lithium carbonate, you can actually also use a whole pile of other salts. You can use sodium-based oxides, potassium-based oxides. We just have found that the best structures come from lithium-based, but it's not actually used up in the system. It's a closed loop. It gets infiltrated with CO2, we pull the CO2 out, and then it gets infiltrated again. And so it's actually being pumped around in a circuit. And so we get oxygen gas as a byproduct, and then we get that solid carbon coming out. Now, to the point of what has been done in the past, what we're building on here, is that people in the past have done basically just these big plates of carbon. And we saw that and said, what if we have a more dynamic process there? What if instead of just building up these essentially random plates of carbon, we actually make that into a dynamic process and pull that carbon out at the same rate it's being bonded on. And some of our IP around the nozzle technology and how that carbon is actually bonding on, we can control the carbon structure that is being bonded onto the end of the fiber, and so that we get the strength. And it's not just a pencil we're extruding, but something that's actually really strong in SP2 configuration. And so that's really where our development is. And kind of the whole system is we take that supplier in, we've got the closed circuit design, and that carbon bonding on at the same rate we're pulling it out. Again, that's kind of where the additive manufacturing robotics comes in. And then that goes to a material that can be utilized by customers. Again, it's a raw material, so it's something that they would integrate.
For the molten salt, I'm just curious, like, is it like, how does it feel like? Is it like viscous material?
Yeah, so
exactly
it's at a fairly high temperature. So it's at 700 degrees Celsius. So it's actually
very hot.
glowing a red hot. Yeah. And that's most of where the energy for the process comes. But it's worth noting that comparative carbon fibers are processed at well over 1,000 degrees Celsius during the carbonation stage. So even though we're hot, we're actually not quite as hot as the comparable carbon fiber. But yeah, it's basically a red hot liquid that you're.
A liquid.
Yeah,
and then viscous.
Yes, it's very viscous. Yeah. Without getting into how we pump it around, it's part of the challenges associated with the process. Is it's a very viscous liquid, and so you have to deal with a very difficult liquid to deal with. But at the same time, you can control the viscosity a little bit with temperature. As you increase temperature, the viscosity goes down, but at the same time, your energy consumption goes up. So the process actually can happen at a lower temperature, 700 C, but that's kind of where we found is the best reaction for our system. Yeah.
Can you describe the additive manufacturing process a little bit so that we understand how that compares to like 3D printing?
Yeah. So it's almost like think of like an inverse additive manufacturing from, say, your 3D printer that you buy off of Amazon or Best Buy, where there you have a filament and then you're melting the filament and then it's going onto the structure. Here we're taking essentially a liquid and then we're making a filament from that liquid. And so it's almost exactly inverse to what you would think of, in that we have, instead of the robotics controlling the extrusion rate of pushing the filament in and then the robotics moving it around, here we have robotics pumping the fluid around and then robotics controlling the rate at which the filament's being pulled out of the solution to match that bonding rate.
And then that filament is chopped or whatever you do with it, and then it goes into the process just like any other.
Yep. So right now, basically right now we have a drop-in solution is really the aim here, so that we're providing something that somebody can literally just drop in or even mix with the existing their existing suppliers of carbon fiber, which I'll get to.
Now, when it's liquid, could you actually do something like a 3D print with it as it's coming out as a liquid instead of turning it into a filament?
Yeah, so there has actually been interest, of the process of controlling how the carbon is being built, of having non-uniform cross sections of the carbon fiber, something like a star pattern. Oak Ridge National Laboratory is interested in that because it's very, very high surface area for some aspects, some technologies that they were looking at. But also you could expand it into making battery electrodes or whatnot. We haven't really dived down that. We're trying to keep our scope and limited resources, time and money just on making the filament, but it certainly could be expanded. Our IP actually covers those expansions. The overarching patent covers that. But for right now, we've just focused on a circular cross-section fiber.
I would also imagine that going straight to 3D printing, it's like at that high of temperature, 700 Celsius, is like very dangerous. And it's too much. I mean, right now, the 3D printers are extruding filaments at 215 Celsius. And it would be probably like...
Yeah, we're not going directly into like a mixed polymer. Here, the temperature is actually it's only a very small section that's that hot. By the time the servo that's actually spinning up the fiber as it comes out, it's only a couple hundred degrees Fahrenheit. So you're talking only about 100 degrees Celsius. Because there's an air gap there. Kind of by design, a lot of servos can't operate at 700 C for a whole slew of reasons. But it is something you could integrate, with an air gap there. But again, we're looking at making a raw material to then provide to the customer for them to choose how they integrate it. Yeah, for sure.
I'm just trying to think of future manufacturing processes.
Yeah.
Does this offer an advantage that so it's interesting.
Yeah, for sure. One of the, I guess I can mention it now, one of the things when we talk about limiting overall cost of both from the manufacturing and transportation, everything like that, one of the discussions that we've had is co-locating with a CO2 producer, like the Cemex plant here in Longmont Lyons, here in Boulder County, produces 300,000 metric tons of CO2 every year in exhaust. And that would be enough to cover more than 30% of the global carbon fiber demand. And so you could co-locate with a producer like that. And instead of transporting, say, gas as your feedstock, transport your finished raw carbon fiber product as your material that you're actually shipping to customers. So we have thought ahead in kind of how we're going to look to expand and actually move up in manufacturing as well. Yeah, so that's a schematic of one of actually our earlier designs. Right now, we produce 8 fibers at 22 centimeters a second, so which is fairly fast. And that's something that would fit. It's about this big right now. Now, up to a manufacturing size, probably something that would be roughly the size of the table, but that would be able to produce about 100 times faster carbon fiber. And it would be multiple reactors all fitting within it. The actual reactors themselves would be about the size of this smaller table in how we've currently designed it. But it's one of the things as we acquire more funding to actually do that scale up. Part of it is working with somebody who has scaled up before. It's not my expertise in scaling up, and so I can do a lot of the design work and math. But working with people that have done that before is a critical hire there. So this is kind of this process that I was just talking about. Right now we sequester at a brewery, so that is a fermentation vessel that you see on the left, and we take that and we compress it. We filter out all the water vapor and particulates, and then we push it into even higher pressure, and then that's injected into the system that you can see in the center there. And that top servo is actually where the fiber is coming out. The piece that you can see, the little black box with the wires going into it at the top, is where the fiber is coming out and being spooled up on the back of that. And then that's something that would then go into some of our customers that we're having really good talks with, including Webasto that was just down in Denver this morning, as well as 3D X-Tech that makes filaments for polymeric carbon fiber. So yeah, that's kind of where our process is right now, that we've proven that we can do it with waste-gas CO2. Initially, we were just doing it with lab-grade CO2, but we've shown that especially with clean exhaust streams, like fermentation exhaust, where you don't have a lot of sulfur-based contaminants and others, we can do the process. And in terms of mechanical properties, we're just about right in the middle of a lot of the mechanical properties of other fibers. One of the things that we've worked really hard on, and we still have a little bit of ways to go, is uniformity of the fiber. Some of that comes down to just funding. It's very expensive to make the nozzles really small and have the robotics be micron scale control. So we do have some variation in our mechanical properties still. But we're excited. We've got some really good results so far. And then the other piece that is important to just mention briefly is our energy use and our CO2 footprint here. And this takes into account the whole polymer process of making the other carbon fibers, all existing carbon fibers, as well as the costs associated with that. The precursor PAN is petrochemical derived. It's very expensive, both from an energy standpoint to make, as well as the whole pyrolysis and carbonization process is very energy intensive. And so that's really what drives a lot of the cost savings, is just a drastic reduction in energy consumption. Of note is that these numbers are from the system we have in the lab right now. So I always like to say, take these with a grain of salt, but this is the data that we have right now, again, at the lab scale. And this IP is having come out of the university. The main overarching patent for the design is filed with the university, but licensed exclusively back to Mach Electric, the company. And it covers both robotics as well as the material science side. So we're pretty excited about that. And, as I mentioned, the lower costs in production and no expensive polymer precursors allow for drastically less energy, less cost, and that translates to advantages for customers, as well as the sustainability advantage of meeting regulation, environmental, as well as qualifying for carbon credits. Kind of our path to market, I won't go too deep into this, but essentially, we've only had, the point right here where we're looking to do initial sales, and we've leveraged a lot of non-dilutive funding so far, both through the state of Colorado and a couple of different universities. And then we're looking to take that to the next step and move all the way up to making large components and hopefully transforming the aerospace industry. And so I talked about a little bit of these as we were kind of going along, but initial suppliers, initial customers, what the beachhead market is right now for low modulus chopped fiber, about 200 million, and with the global carbon fiber market being well over 7 billion, again, growing very rapidly. And some of the major players at the larger scale here being Lockheed Martin, Boeing, and also within the automotive space. We've talked extensively with these four automotive suppliers here, specifically BMW and Volvo and Rivian being very interested. And then we've had some great support on the venture side, and we've got industry mentors forming programs that we've accelerators that we were assigned. So they've been really helpful on that side. And then this is a photo of us with my PhD advisor last year when we won some non-dilutive money that's helped really push this along a lot. So with that, I'll wrap up. And yeah, we're really excited with the progress we've made so far, and hopefully turning all of the carbon fiber in the future and maybe even replacing things like aluminum into waste-gas CO2 derived fibers.
update on the conductive?
Yeah, we're in the process of partnering with the electrical engineering department here. And so we don't have those numbers quite yet, but we're actually very close to getting them. It's a new process for us of testing electrical conductivity. We've just done mechanical testing. But yeah, I guess that's a good point that I'll talk to. Yeah. So one of the, I would say, benefits of the process, because we're doing it via electrolysis, it's actually the conductive pathways that bond these carbon atoms on as we pull the carbon fiber out. And so by nature of the process, the fiber will, according to our models, be much more conductive than other polymer-derived fibers. And that opens a whole new space potentially for use in electronics, power transmission lines, among others, that could be really, really great as a massive technical advantage, and not just a cost saving and environmental saving over existing fibers, but also major technical advantage over. And it's kind of a new idea that we kind of were ruminating on just about was it January, I think, when we started doing that. I was gone the month of February getting married, but we're back in earnest now, doing some of that testing. And hopefully in the next couple of weeks, actually, we'll have some initial results on that. Less stress.
I'll make a quick discussion. So all of the projections for market and initial sales, that's all based on carbon fibers for their
mechanical properties, yeah.
Mechanical and structural properties.
Mm-hmm.
So now we're putting forth, look at this as an electrically conductive material, and it's a whole different market, whole different set of players.
Mm-hmm.
And it's really exciting. So I just want to make that distinction. And we are still getting really significant traction on carbon fibers from a mechanical standpoint, but this is just entirely new, just really exciting.
Yeah.
It would be the first time side effect involved in the center of that.
Yeah, it was something that we didn't even really think of until we were actually doing some customer discovery with Boston Materials, because they use carbon fiber, existing carbon fiber for the semiconductor industry. And their founder was mentioning to us about what our electrical conductivity was, and we just got thinking about it. Like, oh, wow, it might actually. And we did some modeling and whatnot, and there's a distinct potential. I don't put it in yet because we don't have any hard data yet, but it's something we're really, really excited about. Hopefully, getting data that aligns nicely with the models.
Yeah, we're doing it in-house. We've had external discussions with a research group at La Jolla, California, as well as Idaho National Lab. So, we're really happy with how robust our data is going to be when we do present it.
So who in La Jolla?
I think Dr. Chang at UCSD.
Oh, okay.
Material science. It's a material science.
We'll talk. There's some interesting things going on the way.
Okay. Yeah, I mean, it could be a good collaboration. My brother actually lives down there too. I haven't worked with UCSD. I know.
It's kind of the best place to go.
Yeah.
Whenever we go to La Jolla.
Why not Ellis?
Yeah, so one of the things that we're actually going over, we're doing the NSF Nationals I-Core program this summer. And a big piece of the funding that comes along with that is customer discovery. We just haven't had a chance to talk with them yet. So we actually have. Yeah. Mm-hmm. Yep. Absolutely. Yeah, we're planning. So we have $25,000 to spend in like 2 months of customer discovery. So we're hitting it really hard, talking with a lot of customers, and we have a trip planned.
There's a big conference in Paris.
Yeah,
so that would be perfect for us.
Yeah, we've reached out to a bunch. It's the Paris Air Show, talking with a lot. Yeah, it should be good. I think there's a lot of players as well. I have some friends just from PhD that work in some of the defense contractors in Italy, as well as Germany and France. So like Arrain Space, Therium, the DLR, a few others. So yeah, we're looking to definitely expand to the European market as well, especially they're being pushed hard on the regulatory side, as well as for sure.
So another thing I'll mention, and this is just I think, new since we talked, but we had a great discussion with someone who's ultimately not going to place an order, but with Lucid, but it's still beneficial. But we talked with Lucid, and to get one component in a car, they need about 5 tons annually of basically supply chain. So we had like a lot more discussion since we last talked with actual OEMs of like supplying a part and like what actually goes into that. So yeah, obviously we wish we had that contract signed, but it was a really good method of just determining order quantity and what a supplier like an Airbus would look like for.
Yeah.
Like 110 starting there.
Yeah, it's another reason we're looking at some of these milled and chopped fiber markets is because, like say for a 3D printer filament, where they're already mixing in chopped carbon fiber, they can mix in some of our fiber, but it doesn't have to be the whole fraction. It can be 10% or 20%, and we can slowly ramp up our production rate to meet their demands. Whereas if we go straight to a continuous fiber, it has to be the entirety of the part made from that fiber, which means their volumes of production have to be a lot higher. So it's a good beachhead that allows us. Yeah. I mean, that is the goal.
So Ellen, in your lab, saw the carbon wires inside.
Yeah.
So I wonder if we get a sample from these guys to see it.
That would be interesting.
Yeah, to see the difference in how that works.
Do you mix with a polymer?
I think that's the polymer, right? And with one, Centra's working on the multi-material printing.
Yeah.
So to just take whatever is above.
Yeah.
But it's already in the form of a filament.
Okay.
But when it's not in the form of filament, we also have these other 3D printers that we're using to make our own filament. So we mix material together and make our own filament.
Like from pellets?
From it's usually viscous material.
Okay.
So, and it can also be like, if it's powder, it can be mixed with our.
Okay.
We mainly work with biomaterials.
Okay. So like a direct ink writing type printer. I'm familiar with direct ink writing, where it's basically like a liquid and a plunger out.
Yeah, a plunger, and then we have the mixture inside.
Okay. Yeah. Okay. Yeah.
But if that proves interesting, I think it's inclusive. We're interested in getting some fiber to put into a filament to test.
Yeah, definitely. I think we're really excited to get
inside. That was the first time I thought about that. Oh my God, it opens up incredible things you can do with a 3D printer.
Right. Yeah.
And if yours is much better in terms of connectivity, that would make a difference, I would think.
I know we're excited to hopefully get some of this data and matching the modeling and whatnot. So one of the things that I'll say that is also, even if the initial results aren't exactly what we expect, one of the things that's also really beneficial about the system is we can control that electrolysis without going too deep into some of the IP, how the carbon is being formed. So as not only the nozzle, but also the electrolysis signal that's going to the end of the fiber that's actually forming the carbon, there are a few dials that we can turn there that allow the carbon to come out differently. And so to change the properties. It is one thing that typically, if you have a very high strength, you have less stiffness. And so most utilization of carbon fiber wants it to be stiffer rather than stronger. Because at the end of the day, they're going to fracture more than just be pure strength. So stiffness becomes better. And so that's something that we played with originally. Exactly. And so I think there's a lot of opportunity to even push the technical boundary beyond where we are right now to something even better. So, I mean, it's kind of a whole new way of additive manufacturing and utilizing this chemistry. So there's a lot of excitement. We are planning on potentially doing a publication on data, not on the process, but just on the data. And that could also be a way that we're looking to, excite the community and things like that. So
So just publish this performance.
Just performance specs, right? Because that
Don't tell them how you did it. Just
exactly. So yeah, because we don't necessarily need to tell them how we did it on a paper. It can just be these are the performance specs that we're really excited about with a new process. Yeah, yeah, we negate all that risk. So yeah.
Curious about the CO2 part.
Yep.
Do you see this as being like attached to a carbon sequestration system, Iceland or whatever, or like breweries all over the world are going to have these systems, or is it more like we're getting the CO2 from somewhere else?
Yeah. So really how we see it is the most advantageous for both parties, the supplier of the CO2, our feedstock and their waste, as well as us, is to co-locate. And that can be with breweries, although most very large breweries actually recycle their CO2 for carbonation. It's a very expensive process to do that, so smaller breweries don't, but like Course does. However, most heavy industry doesn't capture their CO2 right now. There are existing methods. Actually, if I hop back to, I guess actually in this tech deck it doesn't have it, but there's a startup here in Boulder, late stage startup, I would say. They already have some major facilities, called Ion Clean Energy. And essentially what they do is they have a proprietary process of pulling CO2 basically out of a solvent, so out of a big exhaust stack from whether it's energy generation or concrete generation, large scale ethanol production, other chemicals. That gas flows through essentially an exchanger, and then it absorbs into the solvent, and then they hit the solvent with steam, and then the CO2 comes out of it, and then they just have it in a closed loop cycle. Right now, they just push that CO2 back into the ground. But what we have talked with them about is potentially utilizing some of that CO2 that they get and have that on site because they're capturing that CO2 on site and being essentially another step of the on-site facility at one of these large manufacturing or energy production facilities, and then capturing that there. Direct air capture is an option, but it's something that is definitely much more difficult. Even though the CO2 levels are rising, it's still by parts per million, it's very low. And so pulling it directly off of a producer helps mitigate the environmental impact of that, but also it's from an economic standpoint, it makes a lot more sense to just mitigate it at the source rather than pull it directly out. So we're really focusing on mitigating at the source, things like initially small breweries, just because they're usually easy to work with and they're laid back, but then also moving up to energy production and concrete production, as well as chemical production. Specifically, we've talked with the Cemex plant here. They have more CO2 than we probably could utilize in the near future. But we look to utilize even a fraction of that would be advantageous, and potentially even get paid for it. That's actually not in our economic model either, but especially in areas like Boulder County, where they're receiving a lot of pressure to reduce their emissions, it would be a potential partnership where we would actually monetarily benefit as well from that being on site. Maybe even it was mentioned of having free power, something like that. So, yeah.
So CO2 unique in your process or other things that
That's a good question, actually.
Methane, for example, if you could
methane,
that would be incredible.
So it's something that you could say burn methane beforehand. We actually had a conversation about that with the folks from Ion Clean Energy. There are certain, because that's
you get CO2.
Yeah, exactly. Yeah. They put it through a very clean methane burner, and then essentially split, because when you burn methane purely, you get water vapor and CO2. And so essentially, yeah, that's actually is something that they're looking at doing, and we could be another step on that. So you could take pure methane. One of the things that we haven't explored at all, but is, in the ideas there when we were talking with them, of you could utilize the heat from combusting that methane to run the process too. So there are definitely options that you can drive down the cost drastically Natural gas, for instance, you can burn natural gas to heat the system and then be piping that CO2 directly into as the feedstock itself. We haven't really focused on that yet because our IP is really on the producing the fiber side, but there are a lot of really exciting options there as we scale up or move towards manufacturing, for sure.
Is the future of the carbon fiber space, like it's, I don't know, maybe like 15 years ago, it seemed like there was a lot of hype around everything's going to be carbon fiber. Our cars are going to be entirely carbon fiber. And I'm curious, like,
yeah,
if the market is growing just like 13% or whatever you said.
Yep.
So
yeah,
it's going to be a lot more than that. Is this potentially part of that?
I'll take it first and then I'll tag Wes in here. One of the big things here, it comes down to cost a lot. But also specifically in the automotive space, one of the things we're not looking at is weaving into, say, the safety structure. Now, there are vehicles that do that, very high-end vehicles. There's one mass production vehicle, the BMW i3, that was fully carbon fiber. And part of it is cost of just the fiber itself, but also it's very, very difficult to repair. So if you get into a fender bender with a car and it's just the exterior body panels, then that's very easy. Those are usually replaced anyways, regardless of what they're made of if you get into a fender bender. But if you're talking actual crash structure, it's very difficult to repair that. Essentially, the i3 or the i8 or your Ferrari or whatever gets totaled when you do that. Or they have a very complex process of like cutting it out and you have to take it to somebody special. So the growth of the carbon fiber use isn't really in that crash structure, but it's in all of the other components. Now, within the aerospace sector, it is growing in all the structures. There's a big push right now to not only have the wide bodies be composite, which they already are, but move the narrow body planes, your 737s, your Airbus A320s, A321s, things like that, to composite, starting with just the wings, which would be huge volume. So there is actually massive growth, and those are actively being developed right now, and replacing a lot of aluminum parts as well. The main thing, though, for automotives, you don't see a lot more cars being, the structure itself being made of composite. BMW specifically actually is growing drastically in that still. They've really committed to it, which is part of why we were talking with them. But even they have backed off to the whole vehicle to just specific structural support members being composite. They're a little bit easier to replace, things like that, where instead of a whole side of the car, you just replace that beam. And so that's why likely it will, until a new method of swapping out whole panels becomes developed at the same time, you'll see more just body panels, interiors, seats, subframes, structures like that be made of composite rather than your actual frame that you're jacking your car up on or something like that. But certainly in aerospace and wind energy and other sectors, it is growing drastically.
So that was a great answer. Just to kind of put it in different words, all of the market research that we've done has shown that there's currently a gap between supply and demand. So there's more demand than current supply. So in a lot of use cases, we've had direct customer interviews with OEMs, that there's a lot of use cases where they'd like to use chopped carbon fiber, but it's cost prohibitive. Boeing's echoed that. We've had similar feedback from the automotive industry. Again, just to make sure that we're highlighting certain things, our current go-to-market strategy, and that's totally separate from the electrical conductivity, as we're talking just mechanical properties, is we're doing chopped carbon fiber, and we're speccing it against the most common chopped carbon fiber on the market right now, Zoltech PX35. So on our initial sales call, we're basically just saying, here's the specs for Zoltech's PX35, which you all know and love. Here's us. We're cheaper, we're scaling, and we're also carbon negative, which is important to serve people. So decreasing the price will, in that there's already a surplus of demand, will create a lot of new use cases. Yeah.
By the way, 13% biennial growth rate is a rocket. That's really fast growth. Usually not sustainable very long. So the market is growing really fast.
Yeah.
Just a kind of curiosity question. So the process you started out with had a certain purpose or intent behind it. And is it fundamentally a mechanical application of the fiber?
Yep.
And then coincidentally, it produced a conductive property. So is the connectivity a function of just your process motivated or resulted in an orientation of the molecule such that it was more conductive versus otherwise?
Yeah, so it's actually
what exactly is that orientation? What's the delta? What's the range of orientations or so forth that were available initially?
Yeah, that's actually a really good question. So I'll answer initially in that, let's see if I remember my numbers right. It's 10 to the fourth in terms of is it ohms per meter that the current fibers are right now. 10 to the seventh is like a copper, and a pure carbon fiber would be high 10 to the sixth. So we're about 30% less than a pure copper, but a fraction of the weight. And so we could never be quite as conductive as copper, but conductive enough that you'd be essentially very, very close. You could take that up with clever design of when power's passed through a wire, it's actually not passing uniformly through, it's only on the outside. And so because you can be very strategic in how you're making the fiber and things like that, you can get the effective conductivity roughly the same. And to answer from a material science standpoint, it's all about how the difference of having graphene sheets versus carbon nanotubes, specifically multi-wall carbon nanotubes within the fiber itself. And so we have more carbon nanotubes per cross-sectional area than a comparable fiber. At least that's what the models are showing. And that means that we have more conductivity. Essentially, at the end of the day, a carbon nanotube has more conductive pathways than a graphene sheet that's aligned along the length of the fiber does, mostly because those are broken up and there's more surface area of touching on the carbon nanotubes. And so we have a higher fraction of those. And that's just because how the carbon atoms are actually bonding on, it's the lowest energy pathway to form these multi-wall carbon nanotubes with.
Did the tubes increase surface area because of the tube? Is that correct?
Yes, at a sub-fiber scale. And so we're talking sub-fiber scale right here. So if you had just a pure carbon nanotube, that would be the maximum, just full of carbon nanotubes, that would be the maximum conductivity you can get. And so what we do is essentially have the fibers are a mixture of different carbon structures throughout the cross-sectional area. And we just have more conductive structures basically at the end of the day.
The actual process, so it's the process that results in this structure that have both mechanical and eventually electric. So, but what's distinct about the process that led to this thing? My question, why hasn't this already happened?
Yeah, and so it's actually also a good question. And when we were first initializing it, initiating the project, I guess, it was kind of surprising. But the main reason, and there are a few other companies utilizing this chemistry to make basically, they make these big plates and then they scrape the carbon off of it. A company called Sky Nano is doing that. There's another one, Hydrax in Seattle area, among a few others, C2CNT in Ontario. And essentially their whole business model is around the CO2 capture and creating carbon nanotubes. Carbon nanotube as a powder. There is a market for ground, basically powder carbon nanotubes. It's not nearly as large or economically feasible as carbon fiber. Carbon fiber is much more expansive. And so essentially, at least from what we can see, their business model is more surrounding the carbon sequestration process rather than trying to actually make a new type of carbon fiber, something that already exists, but just from a different process. And so essentially we saw this existing chemistry and saw an opportunity to bring in a way of making this chemistry more useful, which is very common in the academic research community. Is that you're not starting new physics from the ground up. You're building on what others have done and bringing in some novel change. Really, at the end of the day, what we're doing isn't physically, from a physical science perspective, brand new. We're just being very clever with how the reaction is happening, and then creating something more useful from an economic business perspective out of existing chemistry.
I'm sorry for that point.
No, this is good.
Is it correct to say that then the motivation of the process was to produce a fiber as opposed to powder?
Yes.
Is it literally that?
Yeah, in a very simple, very high level ways that we are making, instead of, it doesn't make a powder in the actual reaction. It basically makes this big, net of carbon on a big plate, something that would be, the size of my phone or something. Or I think at production scale, they're much bigger than that. But instead of just making a big plate of random carbon, taking that and saying, okay, we can have it actually a continuous process and pulling the carbon out. Because another aspect is it's a batch process right now. The other way it's done.
So it was the goal of extrusion that motivated the process.
Yeah, I guess you could say that. It kind of came together. The idea kind of came together all at once. Of like, I was familiar with the chemistry, and I've had several years, many years now, actually, background in additive manufacturing. That was a big part of my PhD. And kind of just finding a unique solution to utilizing this chemistry in a what we see as a much better way of utilizing the chemistry to produce a better product.
Carbon fiber isn't made like through it's like, I don't know if it's a wet spinning process.
Yeah, I believe it's done through wet jet.
Wet jet spinning.
Yeah. So essentially, I was actually visiting one of the carbon fiber production facilities in Kentucky, where essentially it's a wet jet of the polymer. It's called polyacrylonitrile. There are others too, but that produces the green fiber. It then goes on a fiber line, which is actually really long, where it's stretched and undergoes cross-linking through UV. And then that goes through pyrolysis, basically a big oven without any oxygen in it that reduces it down into a ceramic. So it decreases the diameter as well. And then that goes through a carbonization process to kind of align those carbon structures in the way you want it. And the whole time it's under tension, varying tensions, things like that. So yeah, it's basically big polymer liquid, and then it's jetted out, and then it goes through that whole
But that's kind of a very common. That's the one.
Very common,
that's like the super common way of making carbon fiber.
Yep, yeah. Any kind of ceramic derived fiber, boron nitride fiber, carbon nitride fiber, oxycarbon fiber, alumina fibers even are all polymer derived.
So in this case, you're just skipping all of those. Like steps.
Yep.
And going straight from the viscous solution into fiber in like a single.
Yep, in a single move. Yeah. So it skips about a dozen steps.
It skips a lot.
Yeah.
I've seen I've seen the guys doing.
Yeah.
It's also not very like health risks are also very high. You have to wear like a lot of.
Yeah, the polymers are nasty.
But then they also smell. There is a lot of research actually happening with like how to cross-link the fibers. Like, you mentioned the UV one, but they are also trying the ones that are like more like oven. Like there's a lot of research trying to minimize risks, energy, and resources along the process rather than like innovating in the actual way of doing the fibers, which I really like about it.
The initial funding for this was on an NSF funding on pre-ceramic polymer derived fibers. So that one kind of focused specifically on carbon nitride fibers, that funding. But this is what that NSF funding kind of kicked off. The original ability to buy some of the materials and things was on the fiber side, polymer derived. And we kind of were thinking, what if you just take a totally new approach at it?
Yeah.
Instead of, kind of getting stuck in the same lane, think outside the box a little bit, but not too outside the box.
Because it still has to fit.
Yeah.
So on the electrical side, you think you're gonna come in close to copper?
So yeah, it would be,
because that's not.
yeah. So
Which isn't remotely.
yeah, it's much lower. Yeah.
Much.
Yeah, so we're hoping to come in about 30% to 50% lower than copper, whereas aluminum lower, yeah. Whereas like aluminum, I believe, is a whole order of magnitude lower.
60.
Yeah. So roughly that. We are hoping to beat aluminum in terms of conductivity. But again, yeah, I guess we'll see. We're excited though. It can't actually reach the conductivity level of copper. Just the physics don't really allow for that. But we're certainly hoping to beat aluminum.
There's a pretty significant loss.
Huge loss, yeah.
And so the dollars of what that electricity is worth. Be interested in that figure.
Yeah. There's a lot of interest right now in that too, especially as the power draw from the grid goes up continuously. So
Thank you.
yeah.